Alright, so a couple students have asked for this video because they missed Friday's class. A little late, but better than never. Let's start out with the mass of our hydrate. So the step-by-step process I go through here is, here's the data I've collected. I've figured out the mass of my glassware, and I know the mass of my glassware and the hydrate. And then after heating, I know the mass of the glassware and the anhydrate. So what I'm going to go ahead and do here is I'm going to start out by figuring out my mass of my hydrate. So to figure out the mass of the hydrate, I'm going to take the mass of the glassware and subtract it from the mass of the glassware and the hydrate. So that's going to be 142.92 grams minus 139.31 grams, which is going to give me a grand total of 3.61 grams. Once I've got that done, it's useful to then figure out the mass of our product, so the glassware and the anhydrate. So this time I'm going to figure out the mass of the anhydrate, so that'd be the CuSO4. And again, we're going to take the mass of our glassware and subtract it from the mass of the glassware and the anhydrate. Seems pretty logical to me. So let's go for it. 141.87 grams subtract 139.31 grams gives us a total of 2.56 grams. Sorry if you don't hear the taps of the calculator, I'm using my notes as a guide. So when you think about it, if you take the mass of the hydrate and subtract the mass of the anhydrate, the difference between the two. So sorry if that jumped there, I just got distracted. If you take the mass of the hydrate and subtract the mass of the anhydrate, you should be able to get the mass of the water, which is the difference between the two when you think about it. So I'm going to go 3.61 grams minus 2.56 grams. Sorry if this is a little bit cluttered. Equals 1.05 grams. So we've now got some numbers. We've got the mass of our hydrate, mass of our anhydrate, the mass of the water. But the question asks us to figure out the percent mass of water in your sample of hydrated copper 2 sulfate. So what we do now is we take our mass of water, and if I was working on a sheet of paper, I'll see if I can do this. I'll try to move the whole thing down now. See if I can scroll down. Oh boy, nope. I'll do this off to the side here. I would work down ideally, but I'm not going to be able to do that, so let's just kind of do this move. So I take my mass of water, which is 1.05 grams, and divide by our total mass of everything all together, which is 3.61 grams, and then I times by 100 to get an average, or a percent by mass of 29.09%, and I've included 4 significant digits there, so that's a good place to be for now. If your answer was a little bit different, well, you got slightly different numbers than I did, but they should be in the same range. So now I need to determine the chemical formula of our copper sulfate hydrate. So we'll have to figure out what the amount or the coefficient for the hydrate is. So N equals, or the N of water is 1.05 grams, which we got from before, and we divide by the molar mass to give us moles. 0.05827 mole, and our amount of copper sulfate is 2.56 grams divided by the molar mass of copper sulfate, which would be 159.62 grams per mole. Gives a total of 0.01604 mole. You'll notice that both times I've written 4 significant digits. Now I'm going to look at our ratio of copper sulfate, and I'll just kind of draw a little divider here. I would space this out more on my sheet of paper when if I was working. To some amount of H2O. So now we use our amounts that we've calculated above, so 0.01604 mole to our amount of water, and don't forget that amount means moles, 0.05827 mole. Now we have to go to lowest terms, so we divide by the smallest number. That's a mole. And, that equals 1. 0.01604 mole. And when I do that math, I get 1 to 3.6. And because in this situation, our anhydrate is always going to be kept as a 1, what's going to happen is we're going to rewrite this and just round 3.6 up to a 1 to 4. And hey, look at that, I'm not perfect either. So that happens that I'm not perfect, and you know, there's a bunch of different reasons why my numbers may have not worked out perfect. So let's just finish off with a therefore statement real quick. Therefore, the formula is CuSO4 tetrahydrate, and we'll get into some of the errors that may have occurred from when I was doing this lab and what I could have done differently to remedy this answer, because we know that the answer should be pentahydrate from the chemical formula itself and from notes that we've done earlier on. So I'll try to handwrite out my answer as best I can and as neatly as I can here. So if not completely reacted, or instead of reacted, we could say the word converted to anhydrous CuSO4, the percent H2O would be, I'm not sure what it would be. And let's, I'm going to leave kind of that blank for right now, and let's just think about it for a second. So if you hadn't heated it completely, and let's say you had leftover mass of water, what would happen? So because the mass of the anhydrous and I'm going to put in quotes because it's not truly anhydrous, we have some mass of water remaining, and what's going to happen is our mass of anhydrous CuSO4 would be higher or increased, and that should seem pretty obvious because of left over H2O, and that leftover H2O would increase the mass. So let's look at an example here. Let's say I did this activity and I got 1.2 grams for my mass of water, and my total mass was 3.5 grams. I times by 100, and in an ideal world I got 34.63%. Hey, that's not bad. You know, the ideal answer is 36.08% would be the perfect answer, but you know, 34.63 is not bad. So let's just label this as our ideal. So let's say this is our ideal. Well, let's now compare this to a situation where we can look at this increased mass. So what would happen is we would do our math at the end, and what would happen is if we had a greater overall mass after doing the work that you guys did earlier, don't forget that you get the mass of water by subtracting the mass of what we think is anhydrous CuSO4 from the mass of the copper, or the hydrous CuSO4. So when you do that, if you do that math and you have a greater amount of CuSO4, the amount of water you're going to get is going to be less. So let's say we get 0.8 grams. What's going to happen in this situation is I'm going to end up getting a percent of 22.86%. And you'll notice that what happens to our overall percent, so this is our ideal, if we ended up leaving some water left over, our overall percent ends up being lower. Whoops. Yikes. So when you leave that water in there, we think that our mass of copper sulfate is higher, which decreases the amount of water we thought that we had boiled off. And what ends up happening is it causes our overall percent to be lower. So suppose you did not completely convert the hydrate to the anhydrous compound. Explain how this would affect the formula we got. Well, the value of X would also be lower, since the amount of the ratio of copper sulfate to water would be affected. So what we would get is the value of X So if you got a ratio of 1 to 2, you really didn't heat enough. If you got 1 to 3, you should have been more patient. 1 to 4, you're not doing bad. And hey, if you got 1 to 5, you're doing pretty well, actually. So I think that a lot of people in the class got in this range here, and so did I. So maybe I should have heated more. That's something that, I guess, being more patient and following instructions more carefully. I know one group used the porcelain and a Bunsen burner, and they got really, really close to 1 to 5. So just that's an option as well. So this example gets a little bit harder to explain. I'm going to start by reviewing and going back to my personal results, and I'm going to get rid of them and then go to this result. So let's say I got I got 3.61 grams as my hydrate. So this is the hydrate and crucible. Just hydrate. And now let's look at this, and we got the CuSO4 to be 2.56 grams. Now let's say in our activity we got, just to figure out our hydrate, I just want to explain this math. 3.61 grams minus 2.56 grams, and then we got our water through that math of 1.05 grams. And I'm just redoing this because it's important to discuss. So let's say instead of heating carefully, I lost some mass as we were going along. And as we were going along, we were losing mass, and as we continue to heat, let's say instead this time we got a mass of, I don't know, let's say I got 2.46. I lost 0.1 grams because of not being careful in heating. So what ends up happening is when I do this math now, I do 2.46 grams, and what does that do to my mass of water? Well, it fools me into thinking that I actually lost a greater mass of water. So by not being careful and losing copper sulfate, it actually compensates in our math, and our math compensates for this and shows us that, or we think that we lost more water, when in reality we're losing amounts of our anhydrate. So I just illustrate this because when I go into this example, I don't want you sitting there going, why is he saying this? And it kind of crazy talks. So let's say, for example, I have let's do some fictional math again, and this time what I'll do is I'll again use my ideal. My ideal would be 1.2 grams divided by 3.5 grams times 100, and that's going to give me 34.63%. I'll just label that as my ideal. And this time, we're going to compare that. And let's then say, well, let's say we weren't careful in our heating. And in our heating, we lost some copper sulfate. And what ends up happening to our overall mass of water? Because remember, this number is our mass of water. This is our total mass. Mass of water, total mass. So we heat too quickly, we lose some amount of copper sulfate, but our math ends up making us think that we've actually lost a greater mass of water. And now our percent jumps up to 42.86%. So now let's make our summary statement that I did before. So if spattering occurred trying to not write like a 2-year-old right now. The percent H2O would, and look at our numbers below here, well, our percent H2O would increase, and because the mass of anhydrate would be less, making the amount or the mass of H2O seem, not really be, but seem higher due to calculations. So if you think back now, if you have a seemingly higher amount of water, what's going to happen to our amounts, well, or our ratio? So instead of having a 1:5, which is ideal, you could, if you really lost a lot of mass, you could get to 1:6 or 1:7, or yikes, I wouldn't even want to imagine what you'd have to do to get to 1:8 in terms of losing mass due to spattering, but that would be really being not careful when you're heating, or perhaps spilling or tipping something, and that would go into the mistake range instead of an error. So as you lost more mass, it would end up increasing the ratio of anhydrate to, or the anhydrous substance to the hydrate.